The fundamental theorem of algebra. Sounds really complicated, but it's not really that much. Basically what the theorem says is this. If f of x is a polynomial of degree n, where n is greater than 0, being some number greater than 0, then the equation f of x equals 0 has at least one root in the set of complex numbers. So you have to understand a lot of vocabulary there. It's a pretty dense statement. But basically what it says is this. If I gave you a polynomial such as x subtract 1 equals 0, let's make it something other than 1. Make x subtract 4 equals 0. Or if I gave you x squared subtract 9 equals 0. Or if I gave you x cubed subtract 27 equals 0. If I gave you any of those, well, if I solve this equation, how many solutions would I have? If you solve this equation, you get x equals 4. The only possible number you can plug into this equation to make this equal to 0 is 4. There are no other numbers that work for it. So in a sense, there's only one solution. And that solution is in a subset of complex numbers. So you understand complex numbers are basically, if you know the definition of it, is basically a real number or an imaginary number. All those numbers fit in a set of complex numbers. So complex numbers by definition is an imaginary number, like I, plus a real number, like 2. So I plus 2 is a complex number. You may see that also as 2 plus I. But technically any number is a complex number. The reason why any number is a complex number, if I just gave you 7, 7 is a real number, however it's also complex because I can add 0i to it. And now it's a real number plus an imaginary number, making it complex. Or if I gave you 2i, it's also a complex number. It's purely imaginary, however I can make it complex simply by adding 0. Now it's the exact same value and it's complex. You have the real number plus an imaginary number. So basically any number is a complex number. So all real numbers are basically a subset of complex numbers. So this would be complex numbers and this would be real numbers. It's within them. All the real numbers are within the set of complex numbers. If that makes sense to you. So anyway, enough with the vocab there. Hope you understand what complex numbers are. But this has one complex solution. If I look at this one, if I solve the equation, added 9 to both sides, you get x squared equals 9. And we have two answers for it. X could be 3 or negative 3. So positive or negative 3. If I plug in 3 and squared it, it's 9. If I plug in negative 3 and squared it, it's also 9. So you get two real solutions. In this case, my degree is 3, so I should have 3 real solutions. And I know one of them is positive 3, and the other 2 are imaginary numbers, which we talked about in the last video. So that has 3 real solutions, or better yet, 3 complex solutions. It only has 1 real solution, but 3 complex solutions. So just understand that. That's all the fundamental theorem of algebra says. It says this degree can basically tell you how many real and imaginary solutions you have. But it says that it has to be pretty much at least that many. Generally going to be equal to the degree though. Well, I shouldn't say generally. The degree, we always tell you number is real and imaginary solutions. So the degree will be equal to its number of complex solutions. So there's no, most of the time, they will always be the exact same thing as your number of complex solutions. And since we're talking about theorems, the rational zero theorem is also a useful one for this lesson. Basically it says is f of x is a polynomial. This is a polynomial. Where we start off a sub n to some degree, all the way down to some constant term where you don't have an x variable. All right, so f of x is some polynomial. Has integers as all of its coefficients. So integer coefficients is important part of that. Then every rational zero of f has the following form. So if I want to find the rational zeros, all the rational zero has the following form. Some fraction, may not be a fraction, may reduce to a whole number, but generally some fraction, where the factor of the constant term, a sub 0, is divided by the factor of the leading coefficient. So basically what I mean is this. I'm going to give you a polynomial. Given the polynomial I'll just write it out. So given the equation f of x equals this polynomial, its possible rational zeros are, ready for this? Well, here it is. Positive negative 1 over 1, positive negative 4 over 1, positive negative 2 over 1, could also be positive negative 1 over 3, positive or negative 4 over 3, or positive or negative 2 over 3. Got a lot of different potential solutions. This is 2, 4, 6, 8, 10, 12. You got 12 potential solutions, and it might not be but one of those that actually is a solution. So if it actually even has a rational solution at all, it's not even guaranteed it even has a rational solution. But if it has one, it would have to be one of these numbers. Must be, no doubt about it. The reason why is it's the factors of the constant term. The constant term in this case is 4, divided by the factors of the leading coefficient. The leading coefficient is 3. So if you think about the constant term, the factors of 4 factors would be 1 and 4, or 2 and 2. And 3 factors would be 1 and 3. So basically I take each of these numbers and divide by each of those numbers with a positive or a negative version of it. So a positive or a negative sign in front. And that's where all these things come from. That's where all those different possible solutions come from. Let's investigate further and actually figure out if any of those are solutions to it. How about this? We actually start a new one. That way I can make sure that we actually have a solution that I want to see. So pause the video, get that as a note. Now I'll actually give you an official full note that actually involves you having to use the fact that these are your possible zeros and finding out which one of them actually are zeros. So pause the video, make sure you get down to theorem, and let's talk about it. So this example says find the rational zeros of this polynomial. So let's list the possible rational zeros. How are we going to list it? Find all the factors of 12, the constant, and find all the factors of 1. 12 has the factors 1 and 12, 2 and 6, 3 and 4, and that's it. 1 has a factor of 1, or 1 and 1. You don't need a second one. Just 1. So we actually set this up. What we're going to actually have is this is the factor of 1. We're actually going to have each of these numbers divided by 1. So my possible zeros are positive negative 1 over 1, positive negative 12 over 1, positive negative 2 over 1, positive negative 6 over 1, positive negative 3 over 1, and positive negative 4 over 1. And that's pretty much it. That's all the factors of 12 there are. So those are all my potential factors. To figure out which one actually is a factor, that goes back to the first day where we learned synthetic division. You could take any of these numbers and divide it into this polynomial and figure out which one actually divides into it evenly. Got a whole lot of numbers to choose from. Pick one. I'm going to start with positive negative 1. This is really just 1, right? So I'm going to start off by taking 1 and using synthetic division to see if my remainder is 0. So we got 1, 2, negative 11, and negative 12. 1 comes down. This is 1. This is 3. This is 3. This is negative 8. This is negative 8. This is negative 20. This is not 0. 1 is thrown out. It doesn't work because remainder is not 0. So that tells me that 1 isn't a 0 and extract 1 is not a factor. So next down is negative 1. Numbers are 1, 2, negative 11, and negative 12. And the 1 comes down. Negative 1, 1, negative 1, negative 12, positive 12, and look, it's 0. My remainder is 0. And that tells me that this is a 0, and it also tells me that x plus 1 is a factor. So if I know that, I can use these numbers to come up with a new polynomial. If you notice, it started off cubed. So this is going to start off as 1 x squared plus 1x subtract 12. At this point, I'm going to assume that you know how to factor. I'm assuming you're going to look at this and you can tell that you can factor it. So this piece factors. It factors to be x plus 4, x subtract 3. And my other factor is x plus 1. So since my goal was to find all the rational zeros, I really can look at this and tell my zeros. You can see 1 0 is negative 1, 1 0 is negative 4, 1 0 is positive 3. So my zeros are negative 1, negative 4, positive 3. I don't know about you, but I just find it amazing that I could take all these different possible solutions and narrow it down to 3 of them by using synthetic division. And sometimes you may have to use synthetic division 3 or 4 or 5 times before you even find one that has a remainder of 0. But you will eventually find one. And you see negative 1 was here. Negative 4 was one of the solutions. It was in this set of numbers. Positive 3 was one of the solutions in that set of numbers. See, we could have went all the way down the list had we not chosen the first one before we found a 0. In other words, it's just a beautiful way of finding answers. We know we could find answers graphically. We know we could find a way of answers factoring if we can factor it. This is another prime example, one that would not be factorable by grouping. So we have to find ways of actually solving it. Now, a couple of days ago, we talked about if I gave you a 0, you can actually do this and then go about factoring it. Well, now I'm not even giving you a 0, but you have to use all the ideas to find what the zeros are. And the idea is the rational root theorem says that, well, if I figure out all the factors of this number and divide by all the factors of that number, eventually I'm going to figure out what the zeros has to be, which is awesome. So now without even giving you a 0 or a factor, you can take this polynomial and you can factor it. And you can figure out what the factors actually are. These will be the factors. These will be the zeros. Okay, let's do another. Okay, so find all the zeros of this polynomial. Pause the video, write down the equation, and you go about what you know to find all the zeros of it. And we'll come together in a few seconds. So right now, pause the video, write it down, see if you can find some zeros. So you should have listed all the factors of 6, all my possible zeros, by finding the factors of 6, factors of 1, and now my possible zeros are positive negative 1 over 1, positive negative 6 over 1, positive or negative 2 over 1, positive or negative 3 over 1. So these are all my possible zeros. Possible rational zeros. So if that's the case, I can start with 1. You know, truthfully, that's a lot of them. And truthfully, at this point, I would really give a quick picture of the graph so I can figure out how to narrow down some of those answers. So you don't want to spend all day just going through every one of those just for the fun of it. Well, we can actually use a graphing calculator to find some of the possible zeros. Let's start by doing that. Let's graph it. Okay, so I went to my graphing calculator. I plugged into the equation, plugged the equation in, and let's hit graph. But look at this. I could tell one of the zeros is at 1, and another 0 is at negative 2. And technically, I know this 0 bounces, so it's 2 of them right there. So let's see if we found all of our zeros. We got 1 0 that's 1, another one is 1, and another one's at negative 2. So we got 3 zeros. How many zeros should we have for this polynomial? Well, it's degree 5, so it must be 5 of them. So we can see 3 real ones. There must be 2 other ones someplace else. So now let's find them. Let's keep this in mind. We had a 0 at negative 2, at 1, and 1. So you have a graph for it right here. You don't need any of this stuff anymore. I need the space more than anything else. And we know zeros are at 1, 1, and negative 2. And we know why the 1 is written twice, because it bounces off the axis. I can use each one of these synthetic division to reduce this polynomial further and further. So let's do that. So when I use synthetic division with 1, I get 0. Now I can use these numbers and the second one. So 1, and the new numbers, 1, negative 1, 7, negative 6, and 0. After using synthetic division again, I reduce it further. Let's do it one more time with a negative 2 with these new numbers. So I wind up with this. I'll start off to the 5th. This answers to the 4th. This answers to the 3rd. That means this answer is squared. So it's 1x squared subtract 2x plus 3. As you can see, this isn't factorable because you can't get 2 numbers multiplied together to be 3 and add to be negative 2. So you got to use quadratic formula. And they're imaginary answers.